Okay, so a quick history of computers. So the very first computer, I would argue, is the abacus. Because think about it, a computer isn't necessarily a Mac. A Mac is a most recent version of a computer. Same thing for Windows, right? But before you had the Mac, before you had Windows, you had the PC, right? And before you had PCs, you had other things along the lines of devices like a calculator. So arguably, is a calculator a computer? And the answer would probably be yes, because it's a limited computer in the sense that it's not going to run an operating system or have word processing, but you can do your input like 2 + 2, and it'll give you output of 4, right? So no one's going to argue that a calculator is a computer. So I guess what begs the question is that, okay, if a calculator is a computer, then is an abacus a computer? Because an abacus also is able to add, right? That's what it's used for adding. However, there's no electricity involved. It is just a bunch of rocks or pebbles onto these grooves or sticks, and you just move them up and down, slide it left to right. And by the position of these pebbles or rocks, you have your input and your output, and then you have your state information, right? So you think about that, this is a very primitive way of saying, yeah, this arguably could be a computer in the sense of what it does, right? It doesn't do it via electricity, it does it using physical objects. So the abacus is 2700 BC, and the earliest known version is Sumerian. So with this, however, I use the word invented in quotes, is because it was invented independently by various civilizations. So everyone had the same idea of, hey, we can keep count by moving rocks left and right and have certain values associated with each positioning. But however, the more traditional concept of a computer didn't really take shape until a couple thousand years later. So in 1642, you have Pascal's adding machine. So this is a mechanical device with mechanical dials on there. So how does this work? And what makes it a machine or make it a computer versus just a nice box with dials on it is that it has a series of metal wheels or dials on the top, numbers 0 through 9. As you rotate the numbers 0 through 9, 360 degrees, it's going to carry over. So for example, if you have the ones and you rotate it from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and you rotate one more time to 10, it's going to carry over to the tens column or the tens dial, get rotated. So this carry mechanism allows you to just rotate things however many times you want, and it'll add. So look at, it can add a pretty large number, right? This is like 10 million or 999 million distinct numbers that can be represented here. So if you rotate it in one direction, it adds. If you rotate it in the other direction, it subtracts. So this is a very clever little device with a carry mechanism that is inherently the first mechanical calculator. So fast forward by a little over 100 years, you have Charles Babbage's difference engine. Instead of just being add or subtract, so now this is designed much more complicated, but it's designed to tabulate polynomial functions. So now we're still doing math, but things got more and more complicated, but it's still physical mechanical calculator. So let's fast forward by another 100 years. We're still mechanical dials, but now it's electricity driving the mechanics. So this is Konrad Zus's Z1 in 1935. So this is an electrically driven mechanical calculator. And it's the first freely programmable calculator that takes input via punch tapes. Fast forward just 10 years, not even 100 years, 10 years now, how rapid things are changed. And we move from the world of mechanical calculators or mechanical computers to digital. So digital computers we have vacuum tubes representing the values 0 and 1, right? So when you think, this Colossus had 1,500 vacuum tubes. Think of a vacuum tube sort of like a light bulb. So if it's on, or it's lit, it has a value 1. If it's unlit, it's a value 0. So it uses these tubes to store states of information. So for example, if you have a single tube, you can represent 2 states of information, on or off. If I give you 2 tubes, then you have 4 combinations, right? It's on, off, on, and on, right? So basically, the more vacuum tubes you have, the more information or states you can represent, and arguably the more powerful your computer is. So in 1943, this is the first vacuum tube computer using vacuum tubes to store digital information of ones and zeros. So around this time, this is where we also have the von Neumann model. So this is the current architecture for even modern computers. So with this model of computers, it's not, again, it's not hardware. This is design of how it's implemented, right? Of how whatever mechanic or hardware you choose to implement this, this is the design philosophy, is that your storage, your program is stored in memory, your data is stored in memory. So your processor goes through the memory, grabs the instruction, and the instruction reads A plus B. Then it goes back to memory to grab A, goes to memory to grab B, adds it, and writes it back out. So this constant going back and forth from memory is called the fetch execute cycle. And that's actually used in every current modern operating system that you're using today. So it originated in 1945. So this is where it's all started. So fast forward another 10 years, and the vacuum tubes gave way to transistors. So transistors, again, similar to vacuum tube, was designed to represent information on or off, 1 and 0. However, transistors were much smaller, and they're cheaper, more reliable, and they're much faster. So that's a common theme you're going to see a lot with computer architecture and hardware, is that essentially they're doing the same thing, except the components are made smaller and faster, so you can do more of the same things quicker. All right, that has been the design for computers for the last 50, 60 years, is we're essentially doing the same thing, but we're trying to do things faster. So fast forward another 10 years, and you see, hey, wait a second. Looks like the transistor's outdated now. Transistors only had their heyday for 10 years before the integrated circuits start making their appearance. So the integrated circuit, you might say, wow, but that looks bigger than a transistor. And that's where I need to correct you. That module you see on the right, it has those little pins coming out, and that big black case it's in, that's just a ceramic heatsink that holds everything in. The actual integrated circuit is in the picture you see between the person's fingertips, right? That circuit is in that little green thing, and on there could be hundreds of thousands, if not millions, of transistors drawn onto that silicon chip. So integrated circuits at this point is a circuit board where transistors are not physical devices that you attach to it, but they're actually drawn with lasers. So lasers actually draw microscopic transistors onto each of these chips. And from 1960s and onward, the integrated circuit became the de facto standard for computers, and all your computer components exist as integrated circuits. So Gordon Moore, the co-founder of Intel, made an observation that roughly every 2 years, he's able to double the number of transistors onto the same amount of space on a circuit. And that's not because they find more ways of cramming it on there. It has to do with advances in science and lasers. Like, for example, the laser technology, lasers are wavelengths of light. So the higher the wavelength, you have the lower, they're able to draw smaller and smaller and smaller things. So that as they improve the lasers, you're able to draw even smaller transistors. So hence, on the same area size, you're able to double or triple, or eventually after 10 years, you just keep doubling every 2 years. You might have well, like 2 to the 5 is 32 times, right? 32 times more processing in 10 short years. So this is, the next graph is a representation of the number of transistors on CPUs over the past 40 years. You notice that, yeah, it sort of follows that trend, that it looks like it's doubling every 2 years. So 2018, if we keep drawing out to 2021, you might notice that the number of transistors start flattening out a little bit, okay? The reason it's flattening out a little bit isn't because, you know, hey, this principle of fitting more things onto the circuit doesn't work. No, it's still the same concept. The problem is that they've been doing that by using lasers to draw things ever smaller. But now you hit the upper limits of physics, is that your wavelength, it doesn't get any smaller. So you can't necessarily draw any smaller. So how do I make a computer faster now if I cannot put more transistors onto the same CPU? And the answer is multi-core CPUs. So in this diagram, you have a multi-core CPU. So what's a multi-core CPU? It's just a CPU that has made up of multiple CPUs. So in this diagram, there's actually 2 CPUs inside this one CPU. So if you have 2 of them in there, does it necessarily mean your computer's twice as fast? Not necessarily. When you have multi-core CPUs, the benefit would be if you have, or you're multitasking, you have multiple applications running. So for example, one CPU can be dedicated to streaming a video. Another CPU could be dedicated to your web page. A third CPU could be dedicated to your word processing. A fourth could be dedicated to whatever else. So the more CPUs you have, the more simultaneous applications you can have running. So, but however, if you only have one application running, you're not, unless the application is written to be multi-thread and use all the CPUs, you're not going to see a huge performance gain. Okay, so the biggest benefit of multi-core CPUs really has to do not with making one application faster, but really allowing you to run more applications simultaneously. All right, and actually you even see that even on web pages. A single web page, even though it's like a browser, it's not a single page that's loaded. You might notice that it loads a page and each image and each object is downloaded separately. Okay, just keep that in mind. All right, so let's take a big step back from this microscopic and take a look at from a high level standpoint. How do you interact with a PC? Oh, I'm sorry, it seems like someone has a question. Go ahead.
So with a multi-core CPU, how do we address the issue of increasing speed?
Well, last time you checked, how fast was your CPU? How many gigahertz is it? I bet you it's like 3, 2, 3, right? It's not going to be 10.
Mm-hmm.
Right, but it's been 2-3 gigahertz for the last 10 years.
So you're saying we actually, so you're saying with the frequency of the
has not gone up, has it?
Right, but you said that the point of the multi-core was to get around that
by having multiple CPUs operating simultaneously.
But that still doesn't address the issue of speed.
Yes, it does. If right now your operating system, how many separate things are running simultaneously?
Oh, so that's considered speed of the ability
yeah,
to
because if you only had a single CPU, that one CPU would have to share the load on the 5 applications.
I see.
Right?
Yeah. Mm-hmm.
Think about it. It's like the CPU says, okay, let me work 20% here, stop what I'm doing, 20% here, stop what I'm doing, 20, basically sharing the load from 5 applications. Now you're dedicating a CPU to each one of the applications. Does that make sense?
But the gigahertz will likely not increase anymore.
Well, no, it hasn't. I'm not a hardware engineer. I'm just making observation. Have you noticed it hasn't really gotten much faster? They find more ways to make it efficient, right? But as far as pure raw speed, no. Gigahertz been stuck at, I think, 3 gigahertz for a while now.
Mm-hmm. I see. Thank you.
Yeah, no problem. All right, does someone else have a question? Okay, so moving on. We have, in 1981, this is the first IBM PC. So it's a nice little gray box, gray/beige box. It had 16 watt. This is state of the art, by the way, is 16 colors on that low resolution 640 by 200 screen. So it's text only. The memory is measured in kilobytes, and their storage is a floppy drive that you push in and out. 10 years later, look at the form factor. Laptops became state of the art in 10 short years. And instead of big blocky monitor, you have LCDs, right? And the speed is 25 megahertz. So again, this is a order of magnitude faster. What's hidden here is that megahertz is just how fast a processor runs per clock cycle, but it's actually doing more per clock cycle as well. Memory is no longer measured in kilobytes. It's megabytes now. So we went from thousands of bytes to millions of bytes. So memory storage increased by an order of magnitude, 1,000 times in 10 years, 1,000-time increase. Storage, it went from kilobytes also to megabytes, and also not only to store more, but it uses magnetic hard drives. So speed-wise increased by 100-fold. And for video, you'd have double the resolution and 16 times the color, right? So a lot more colors in much, much smaller form factor. Now you fast forward by another 15 years, state of the art became a handheld. And now the megahertz is a few hundred, but look at the storage. The storage now is measured in gigabytes. So the gigabytes is billions of bytes versus megabytes. So again, 1,000-time increase in storage. And if we look at this little iPhone that we have a picture of it, there's more processing power in that phone in that person's hand than the computers that put man on the moon in the 60s. So that's just put things in context of how quickly things have evolved and how fast. All right. So the current state of a computer, what's after handheld? Well, nothing. I would say that you have a new way of interacting with a computer. You're pretty much everything we cover so far. You still see your desktops, you still see your laptops, you still see your tablets, you still see your phones, right? So what changed? Is that for the last 10 years or 15 years, the computer has moved from your device that you're in your hand and moved into the cloud. So what do I mean by it moved into the cloud? Is that your computer is become a very nice front end or edge device that's used to interact or interface with a computer, right? You have your touch screens, you have your mouse, you have your keyboard, you have your monitor, you have your touch screens or whatever. So all this is good, but however, when you interact with it, where's the actual processing taking place? You might find that we're using Office 365. Where is that? That's actually an application in the cloud. We're using Google Docs. That's in the cloud. When you ask your Alexa or Siri about the weather in San Francisco, does your phone really know the weather? It doesn't. All your phone is doing is recording, capturing your voice, taking the recording and translate the recording into text, and then uploads the text to the server, and the server will get the text, and then it's going to do natural language processing to figure out what you want, what's your intent of your question. And they figure out, oh, you wanted to know the weather in San Francisco. And then once it does that, it goes and queries a weather server, it queries whatever to get the information. And then it does text to, it sends the information back to your forms a sentence out of it, again, using natural language processing. And it sends that back to your phone, and your phone does text to speech by saying the weather in San Francisco is, and then you'll say it out. So all this takes place within a second or two. So, but none of this, very little of it, I would say none, very little of it, the processing takes place on your phone or your laptop, because all your laptop is doing is capturing your input and it's passing the information onto the cloud, where it's more specifically a server on the cloud that's probably hooked up to 1,000 other servers. And then it collects that information and all the details associated with that information and figures out what you want and does something and sends the results back to you. So that's where we're currently at right now, is that cloud computing is pervasive, right? It's everywhere. Is that very seldom do you ever have a device that's useful, that's disconnected, right? If you have an iPhone that for whatever reason has no signal, it's pretty much a brick. It's just, you're not gonna be able to use it very much. So again, that's why we want to reiterate that. That's what I mean by cloud computing, is that the computer now is really in the cloud. Okay, so what's next? So again, there's a lot of people who try to predict the future, but from a computer standpoint, I believe that from a computer architecture or paradigm for computing going forward, it's probably quantum computers. So quantum computers different from how we have approached computers or the concept of storage or compute information for the last 1,000 years. Because in the past, it's always been classic bit, right? If you look at this diagram, you either have a 0 or 1, right? So either it's positive or negative, on or off, and then your computer is based on how many bits of information you can store. So if you have 10 bits, then it's 2 to the 10 possible permutations. So at any given time, your computer can process that much information. However, how's it different from a quantum computer? Well, a quantum computer behaves on the subatomic scale, where things don't always have 0 or 1. In fact, quantum computing exists on 2 quantum phenomena. The first is superposition. Superposition is the observed phenomena where a quantum bit, or also called a qubit, isn't 0 or 1, but it actually is both 0 or 1. It actually has both values. And then it will collapse into one of the values upon observation. So that just means that if a computer is built on n quantum bits, it's technically possible to represent all of 2 to the n permutations at once. So that's very, for most people, it's very hard to grasp that. So it uses superposition because it can represent everything. And upon observing it, it will collapse into one of the values. So how do I know which value it is? So to do that, you have the other phenomenon, which is entanglement, is that I don't need to directly observe this quantum bit. I can observe the other one, its behavior. Once this collapses, the other one will collapse, allowing me to observe it. So this is actually very theoretical at this point. Even though there are some quantum computers that are currently built, but you're not likely to see one being sold at Best Buy in the next 10 years. The reason being is that the hardware necessary to implement a quantum computer is subatomic particles. Subatomic particles tend not to exist in nature readily. Many times you're going to find that they only exist for a few seconds, and not only do they exist for a few seconds, but they exist in a few seconds only under absolute 0 temperatures. So again, it's not something that you can walk around in. Many times you want to look at a quantum computer. There are quantum computers available right now. They're not huge, but in terms of processing, but they will end up taking up the entire floor of a building because of the environment that needs to set up to preserve the quantum bits. Okay, so what are the practical applications of this? Is that a quantum computer is very fast at doing sort of calculations. So if you want to do modeling of weather, fantastic. Modeling of finance, perfect. Medicine, drug, pharmaceutical, fantastic. AI, amazing. If you could do that, that would be amazing because so many different. However, playing videos, no, you see no benefit for doing that because it's those are not as intensive calculations as that will be needed. And the last but not least is encryption and security. Because once you have quantum bits, that means that I can go through every permutation of a 256 bit encryption scheme, break it within like a few seconds. Then that means that I'm going to need a quantum bit to encrypt it in the first place. Okay. All right. With that being said, that is all we have for the class today. Does anyone have any questions?
Yeah, Professor. Question. What is the can you explain the work sets again? Sorry, I went away for a minute.
The work sets will just be a bunch of review sheets that you'll need to do before your exam. And you don't have to do it for another month.
Oh, okay, sounds good. And Professor, no.
Professor?
Yes, go ahead.
Will you post these PowerPoints?
Yes, they should be, the lecture slides should be available on Blackboard. If they're not
Okay.
there, I'll make sure to put it there later.
Are they generally available before class as well?
Yes, generally speaking, they would be, yes.
Okay, thank you.
All right, any other questions? All right,
Oh,
if no other
actually,
questions, then thank
Professor,
you guys. Oh, there is a question, go ahead.
it's more about switching class, changing my class to because I work Tuesdays, Thursdays, and I had to leave work early in order for me to make this class. I know you have class on Monday, Wednesday. Would it be possible for me to transfer over to that class or no?
Yeah, yes, you can do it, but you have to take exams with this class. Because you're enrolled in this one.
Okay, so okay, so how would I be able to get the access to that class then?
Just email me afterwards.
All right, sounds good. Thank you.
Okay, all
Professor?
right, yes.
You mentioned that we should use the first textbook if we're going over the topics that you listed.
Yeah, it's helpful. You don't have to.
Okay, so but generally what we do in class should be enough.
Correct, yes.
Okay, thank you.
All right, any other questions? All right, if no questions, then thank you, everyone. We will see you on Thursday. All right, have a good night.
Thank you, Professor.
All right, have a good one. Thanks.
Thank you, Professor.
Thanks. Have a good night.